thanks for watching, and today I want to present you one of my favorite theorems in complex analysis, or it's more one of my theorems that has my favorite proof using complex analysis. You'll see what I mean by that. Namely, I want to prove the fundamental theorem of algebra. That's algebra, man. Okay, FTA. Not to be confused with GTA, okay? So what does it say? It simply says every polynomial that is non-constant, so every non-constant polynomial with complex coefficients has a root in C. So every polynomial P of Z has a root in C, namely at a 0. Completely algebraic statement, and it's not clear how you use analysis for it, but there's a very neat analysis proof for it, and it has to do with Liouville's theorem. So fact, and I will prove this in the end if you're still interested. Namely, suppose you have a function, a complex function that's differentiable. So if f of z is differentiable and bounded, meaning that so the absolute value of c is always less than or equal to some constant, then f is constant. I'll give you a couple of seconds to absorb the amazingness of this fact. In other words, if you have a non-constant differentiable function, then it has to blow up. So it has to go to infinity, either at a point or at infinity. And this is very not true for real analysis. Because, for example, arctangent is a function that's bounded by pi over 2, but that's differentiable, but of course it's not constant. Otherwise, p-point calculus wouldn't suffer that much, okay? So we will use Liouville's theorem to show that somehow every polynomial that's not constant has to have a root in C. So here's the proof. So suppose you have a polynomial. So suppose you have P of Z equals to an z to the n plus, I guess, an minus 1 z to the n minus 1 plus blah 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 plus a0. And suppose this is 0. And of course, the way I defined it, the highest coefficient the leading coefficient has to be non-zero. 0, and of course n is greater or equal to 1 because we have a non-constant polynomial. And what we have to show is that p has a 0. Question, does the leading coefficient really matter? What happens if we have 2z to the n plus blah blah blah? Just divide everything by 2. You still get that this is 0, and the leading coefficient is 1. So without loss of generality, an equals to 1. So in other words, ignore that. And so p of z is z to the n plus a to the n minus 1, z to the n minus 1 plus blah 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 plus a0 equals to 0. Okay, so we're going to assume this. And for this, we have to use a proof by contradiction. Namely, suppose this is a magic polynomial that has no zeros. So suppose P has no zeros. Well, if it has no zeros, then we can just divide by P. and we wouldn't run into trouble of having singularities. Then consider the following function, g of z, which is 1 over p of z. In other words, 1 over z to the n plus dot 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 plus a0. Again, remember, p is this magic polynomial that has no zeros, so we have no singularities in the denominator, and therefore g is differentiable. So note, g is differentiable because by the chain rule, the complex chain rule, g prime of z is 1 over p of z squared, so minus 1 over p of z squared times p prime of z. The only issue would be if the denominator were non-zero, but we don't have this problem because the denominator is non-zero. So g is differentiable, and to use this Liouville's theorem, we just have to show that somehow g is bounded. So show g is bounded. And for this, notice that we can write g as follows. And by the way, we will assume z is very big, so there won't be a problem. Take this polynomial, just factor out 1 over z to the n. So g is just 1 over z to the n times 1 plus, I guess, z to the n minus 1 over z, so a to the n minus 1 over z plus dot 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 plus a0 over z to the n. In particular, if you take the absolute value of g of z is 1 over absolute value of z to the n, and absolute value of this junk, 1 plus a to the n minus 1 over z plus dot 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 plus a0 over z to the n. Okay, and what I'm really saying is this term doesn't really matter because what happens as z goes to infinity, at least in absolute value? Well, this term goes to 0, this term goes to 0, this term goes to 0, so really the whole term goes to 1 as z goes to infinity. So this thing, as z goes to infinity, goes to 1. What does that mean for something to go to 1? It really means for z large enough, we can make this bigger than 1/2. Because if something, the limit is 1, it's very close to 1, think like 0.999. So in particular, we can make this greater than 1/2. So for r large enough, so for some r large enough, if z is greater than r in absolute value, then this whole junk can be made greater than 1/2. Again, because the limit is 1. So then this thing goes to is greater than 1/2. And again, if you want to be super rigorous, you can use a reverse triangle inequality a bunch of times, but then it feels silly because it's the same argument. Okay, in particular, this is greater than 1/2, so 1 over that, 1 plus dot dot dot, is less than 2. And not only that, if z is greater than r, then 1 over z to the n is less than 1 over r to the n. So if you take the absolute value of g of z, at least if z is large enough, so for z greater than r, h of z is less than 1 over r to the n times 2. And that's 2 over r to the n. And well, if r is large enough, you can make this less than 1. Again, if r is large. Bit lazy here, but you can just choose r to be greater than the nth root of 2, and then that's true. So it's good. In other words, this polynomial, at least sort of at infinity, it doesn't blow up. That's good news. But the question is, what happens if z is small? Well, even better news. Moreover, sorry, I used h, I meant to say g. Moreover, if z is less than or equal to r, then what we have, we simply have a continuous function on a compact set. So this is g on this compact set. Then, since g is continuous, and I guess the ball, so B0R, which I guess maybe closure is just the set of z such that z is less than or equal to r. In absolute value, this is compact. It's closed and bounded here. Then, if you have a continuous function on a compact set, then it has to have a maximum. I guess the modulus has to have a maximum. We get that what's called so g of z is less than or equal to c on that ball for some constant c. Constant c greater or equal to 0. In other words, if z is relatively small, so if z is less than or equal to r, our function is also bounded. So really the picture that we have, if you want to sort of write g, at least the modulus, versus the modulus of z, what do we have? If r is large enough, our function is this thing is at least less than or equal to 1, and for small r, like if z is less than or equal to r, it might be bigger, but it's still less than or equal to a constant. So, in particular, if you choose the new constant to be the maximum of the two, then our function is in fact bounded. So, in fact, g of z is less than or equal to c prime, where c prime is the maximum of c and 1. And so what do we have? G is bounded and differentiable. So by Liouville, g is a constant. But what was g? It was 1 over p. And that's a constant. Again, maybe different constants. So p of z is also constant. And that's a contradiction because remember we assumed that p was not a constant. So in other words, we've shown that we have a contradiction with the fact that p does not have a 0. So in fact, p, this arbitrary polynomial, has to have a 0 somewhere. So again, a purely algebraic proof, but with a purely algebraic statement, but with an analysis proof. I like that because we're like invading into algebra territory and stealing some of this stuff. You know, it's harder to do the opposite, like give an algebraic proof for an analytic statement. But again, that's analysis for you. Okay, you can either quit now if you want, or if you want, stick around and I give you a quick proof of Liouville's theorem. So proof of Liouville. What does it say? Again, if you have a function that's differentiable and that it's bounded, then f is constant. By the way, I met some guy once from Louisville, and I thought it was Liouville, and I told you, haha, is you see the differentiable and bounded? But he didn't get the joke. But anyway, so Liouville is not Louisville, that's what I learned. But anyway, so how do you show this statement? There's this amazing thing called the Cauchy integral formula, which I'll probably do a video on. So, and what's nice is that it relates f, or its derivative, with an integral. So by Cauchy, if you have a random point z0, again random, you can write this as 1 over 2 pi I of the integral over the boundary of the ball and some radius r, any radius in fact. So if this is z0 and this is a radius, the boundary is just the sphere, if you want, of z0 r, of the following thing. So f of z dz, except you add a little singularity, z minus z0 squared. Yes. Kind of interesting. So you relate f prime with an integral over f over a over like double singularity, if you want. And this is like the thing that makes complex analysis work. So all the beautiful facts are because of that Cauchy integral formula. And now, in fact, let me show you how we can show that it's constant. Now, take the absolute value of f prime. Well, that means you take the absolute value of this whole thing. Absolute value, I guess, let me write that down. That equals to absolute value, 1 over 2 pi I, absolute value of that integral, f of z minus z0 squared dz. 2 pi I, purely imaginary, so the absolute value is 1 over 2 pi. And we want to put the absolute value inside the integral, not a problem. dz0r, absolute value of that, absolute value of z minus z0 squared dz. And in general, this integral is badly behaved, but remember now that f is bounded above, so it's less than or equal to a constant. So this equals to that same constant over 2 pi, integral over that, I don't know why I call it sphere, it's just a circle really. And now remember, what was this boundary of this ball? We know it's the set of points whose distance from z0 is r. So, in particular, absolute value of z minus z0 squared, that is r squared. So that's 1 over r squared dz. This also comes out, and you have c over 2 pi r squared. Integral of 1 z0 r of 1 dz. And well, the integral of 1 is just the size of this sphere, or the size of this, I guess the perimeter of this circle, which is just 2 pi r. So you get c over 2 pi r squared times 2 pi r. And you cancel that out, the r cancels out, and you have c over r. So f prime of z0 we've shown that it's less than or equal to C over R. And remember, this C, it was just the bound on F, and it doesn't depend on Z naught at all. Moreover, this R also doesn't depend on Z naught, so you can actually just let R go to infinity, and you get that this is less than or equal to 0. So this constant F prime of Z naught, it has modulus 0. So F prime of Z naught equals to 0. And remember, Z naught was arbitrary, so F prime equals to 0. So in fact, F is constant. How neat is that? So using this beautiful Cauchy integral formula, we've shown that a differentiable and bounded function has to be constant. And I invite you to take complex analysis. It's filled with those beautiful proofs. So I know my eyes are sparkling right now. But anyway, if you want to see more math fun and more complex analysis, please make sure to subscribe to my channel. Thank you very much.